In today's tutorial, we will discuss the four principal mechanisms of nucleophilic substitution. In the preceding video, we have already seen the general equations of a nucleophilic substitution. Either we start with a charge neutral nucleophile. E is the electrophilic center of the second starting material. X is the leaving group, and in this case the bond between the nucleophile, the former nucleophilic part, and the former electrophilic part will be formed. The nucleophilic part will carry a cationic charge, and we will have this X as a counter anion. Starting with a negatively charged nucleophile will lead to a charge neutral product. One example for this case we have already drawn here. So, for instance, we start with ammonia and let this react with methyl iodide. What will happen? The nucleophilic center with its free electron pair will approach the electrophilic center, and while the nitrogen-carbon bond is built up, the carbon iodide bond is broken, forming this ammonium salt as the final product. This is called an SN2 reaction. The 2 symbolizes that for the rate determining step, 2 reaction partners are involved. The rate determining step is dependent on the concentration of the 2 reaction partners. Important is that here we have a so-called transition state and not a reactive intermediate. Let's have a look for an SN1 reaction where we have a reactive intermediate. Well, for instance, let's take again ammonia, but as the electrophile benzyl iodide. This makes a difference since in polar solvents then the benzyl iodide might form 2 ions. The benzylic cation, which is mesomerically stabilized and still in close proximity but solvated by the polar solvent, we have the counter anion. This is then a reactive intermediate. So, first the carbon iodide bond is broken, and then the bond between the nitrogen and the benzylic position is formed. As the final product, we will also get to an ammonium salt. Let's have a look to a very special case of an SN2 reaction which runs via a reactive intermediate, not a transition state. Well, this is every now and then the case. If not, a carbon is the reactive center, the electrophilic reactive center, but a heteroatom. For instance, as a nucleophile, we have, for instance, an organolithium compound. As the electrophile, a bromobenzene. The final product will be the lithiated benzene and the alkyl bromide. Well, this type of reaction is called a permutational interconversion, and well, it might be useful or is useful if we need a lithiated aromatic species. So, how does this reaction proceed? The nucleophile will attack the bromide, and as an intermediate, we will have a bromide with 2 bonds, 3 electron pairs, and overall it is charged negatively with a lithium plus in close proximity. So first the carbon bromide bond is formed, and afterwards the bromide phenyl bond is broken, and this is intercepted by the lithium plus, which ends up at the phenyl ring. Okay, final example and the fourth principal mechanism runs via an addition-elimination process. This is typical if the nucleophilic substitution takes place not at an sp3 hybridized center, but at an SN2 hybridized center. For instance, let's take an acyl chloride and an alcoholate. Then this will react as a nucleophile here at the electrophilic carbonyl carbon. An addition takes place first, followed by an elimination, and in this case an ester is formed. And a chloride anion, of course, we will have a counter-cation present here, also here, and finally there sodium chloride as the elimination product. Thanks for listening.